Hello, this is Professor Mart, and this is exponents. Let's start with the terminology coefficients. When we add something multiple many times, adding apple to apple to apple 4 times, then we write it as 4 times apple. The number in the front is called coefficient. But if we are multiplying the apples together, 4 of them, then we write a number of times the repetition of the multiplications as so-called exponents, as in this case 4, we're writing the upper corners, and this is the number we want to talk about. And to make this sentence more complete, when we say add x, when we add item x is added to what? How do I start out? Well, with an x added, one single x added to what? So to make this complete, we add it to 0. So we start with 0. How many times you add x to 0? That's the coefficient. And similarly, that how many times we multiply to 1, that's what we call the exponents. It's the number of times we multiply x to the number 1. In particular, this gives us a very nice following. Anything to the 0 power, that means there's no apple here. And what we're left with 1. Okay, so anything to the 0, x to the 0 is 1. Here's the formal definitions of exponents. When we multiply the quantity, a quantity a to the number 1 repeatedly, and the number of times, let's say it's n times, we write it as a to the nth power. And this exponential notation works very well when we multiply, divide, and taking powers. So when we multiply, we add the exponents. When we divide, we subtract. So that's why we have names for this rule. Divide, we subtract. When we're taking powers of powers, we multiply. So for example, a squared times a to the 4th. 5 to the square times 5 to the 4th. We are tracking how many copies of 5s. And altogether, multiply the 6 copies. Divide, similarly, we subtract. We are tracking the number of copies because now this basically, now this is saying there are 5 5s upstairs with S, but let's close it up. And we cancel 2 copies. The 2 copies are canceled, hence we subtract, and that's 5 minus 2. So we have 3 copies left. And similarly, when we multiply a power to another, when we raise to another power, that we can multiply the exponent. Here there are 2 2's, but we multiply 3 sets of these parentheses with the 2 2's in there. They all multiplying. So all together there are 6 copies. So hence there's 2 to the 6th and 3 to the 12th. And this is this particular rule. Okay. So these exponential rules, actually exponential notations with these rules make them quite easy to operate. Keep tracks how what is multiplied to what, how many times. But remember, this rule does not apply for add or subtracts. So, okay, in particular, a plus b squaring that, it's not going to be just by squaring a plus squaring b. Okay, a common mistake. That's because there's something else attached. There's a middle term to ab when I square this. Okay, so remember that. Now we come to these special exponents. Okay, it doesn't quite make sense until we make the notation make sense. For instance, what's a to the 0 power? Oh, if you remember, we already talk about a to the 0. It's 1. But here is another reasoning. Okay, how do we get a to the 0 power? We divide a by a because that's 1. But on the other hand, when we divide a by a, we subtract the exponents. Now I'm going to get the exponent 0. So 1 is the same as a to the 0. How about negative power? Negative powers means to flip, okay, or reciprocate. Reciprocate. Okay. So, for example, 3 to the minus 1 means 3 to the 1 is one thing. That means to flip it downstairs. Okay, if 3 to the minus 2, then I will flip the 3 squared down below. So the negative power means to flip. Why? Well, because if I look at the flip of a to the power k, 1 is a to the 0. So I can write that as divisions in base a, but then according to the division, I subtract the exponent. So 0 minus k is exponent, and that's why I get negative k power. So read this backward. Negative k means came from 1 divided by a to the k. It's the same. So negative power means to flip, reciprocate. How about half power? Notice if half power is square root. Why? Because if I square both sides, I get the same thing. So therefore they're the same. Okay. Similarly, if this weren't half, this is the number 1/3 power, that I'll be talking cube root, because if I cube both this a to the 1/3 and take the third power of cube root, I get a again, the same both sides. So half power is square root. And 1 over nth power means nth root. Because I raise to the nth power, I get the same thing. And I get n. Okay. So 1 over n is the nth root. So how do we read fractional power? We read fractional power by always reading the denominator first. Okay. 64 half means square root. 1/3 power means cube root. 1/3 power of 64 is 4. And what happens if I have a combination of something like this? 64 to the 1/2. Okay, I know it's 8, but what happens if I put minus sign in front of it? That means you take the 8, which is 64 to the 1/2, if you like, and put it downstairs. In general, if I have a fraction a divided by b, I raise to the minus 1 power, it means just flip it. It becomes b over a. Okay, so that's a convenient little trick. If I need to change the writing into a fraction, I can use in the form that's useful sometimes. How about these combinations of everything? Well, how do I read these fractional power? Well, in this case, we start out with reading the root first. Always starts out with, okay. In this case, it's a take the nth root. After you take the nth root, then raise it back out to the kth power, plus or minus. Okay. So for example, I have all these fractional power, and how do I interpret them? Well, this is a square root. That's a cube root. And this problem is a 4th root. Okay, so take that root first. And then you raise back to the power -3, the numerator powers. And the square root of 9 is 3. 3 to the 3rd is 27. But then the minus sign says, oh, flip it. Okay, so I read 3 to the 3rd power, then finally read the minus sign, and that says flip it. So similarly, for part B, it says take the 3rd root of 27. Okay, then raise to -2 power. And this, of course, 3. And 3 to the -2 is 3 to the 2 is 9. Then flip it, 1/9. Similarly, this is asked us to take the 4th root afterwards cube it, third power it, and afterward flip it. So 2 to the third flipped, 1/8. Okay. These exponents, fractional exponents, also can be collected when we multiply these roots. Multiply, we add exponents, divide, we subtract exponents, etc. Are still true, even when we use fractional power. So this question asks us to collect all the powers together. Okay, and so don't convert everything to cube root or square root. No, that's not the problem it's asking. The problem asks you just collect the exponents using these rules we have before. So the first one we see is powers to power, we multiply power. So I will resolve the parentheses power as x to the 2/3, multiply the exponents in y to the 3rd power. Next, I'll resolve or collect, make things easier, collect the x multiply, we add exponents. So it's 1 plus 2/3, 5/3. Okay. And next, we finally deal with dividing, and which is subtraction in exponents. So we subtract the exponents respectively. So the whole problem is a fractional calculation of the exponents. And now it collected into these fractional notations. Okay. This convenience of using the fractional notation is to do fractional operations. Okay, instead of using the radical, because fractional exponents are radicals, but it's difficult to use radicals to manipulate the calculation. That's why we change to fractional exponents, make the calculation easier. So for instance, with this one, first of all, we square root of 5/3, and to convert it into the fractional exponents, first notice the square root. So the denominator is 2 and the cube is later. Okay. And this is the square root of 9a squared, and square root of 9a squared is 3a. Okay, assume a is positive. And square root of 9 plus a squared is the parentheses to have power. And we stop here. This is not 3 plus a. Okay. Again, these rules apply, simplifications apply when it's multiplications. 3 times a, but not 4 plus. Now, here is we can use fractional exponents to collect these roots. So, and these are 2 different type of roots, 3rd root and 4th root, and multiply. And using fractional exponents, we can collect them into one single radical. How? Convert them into fractions. The exponents, the radicals into fractions. And then since we're multiplying, we add the exponents. And this is just adding fractions, and this common denominator is a 12, and then you want to 11, 12. So this is the 12th root, okay, of a to the 11th power. So this, we can use fraction notation to kind of collect and connect roots, different order of roots. How about decimal exponents? 0.1 power. Well, decimals are fractions. So we convert them into fraction first. Once it's into fraction, then it makes sense. Or this one, 1.53 half, and therefore, oh, this is square root of 9. So we take the square root of 9 raised to -3, and that's 127. 0.75, 3/4. So that's the 4th root of 16. Then raised to -3. 4th root of 16 is 2. 2 to the -3 is 8 foot to the 3rd power. So that's 1/8. 3 to the 0.4, that's 3 to the 2/5. And I don't know what 3 to the 5th power. So this is a calculator problem. Okay. One thing about decimal exponents, due to the interpretations of changing that into fractions, to make things logically tight, one requirement is we require the base to be positive. Okay, or sometimes we run into problems defining what fractional power is. So we assume the base is positive when we talk about decimal exponents. And finally, there's an important list of powers of tens that the exponent actually keep tracks of how many zeros. Okay, so 10 to the 0 power is 1, 10 to the first power is 10. Okay, and if you probably know these 10 to the power, 10 to different powers, they are called scientific notation. They're very important in science. 10 squared means that 2 zeros behind it. 10 cubed, there's 3 zeros. When we go to negative exponents, we means divide by 10 means 1/10, 0.1. 1 divided by 10 again is 100, 0.01, and then divided by 10 again, 0.01. And just want to make note of in the positive exponents, the number is the same as the number of zeros behind one. But for the negative exponents, we're dividing by 0, so that's the zeros in front of the 1. Okay, including you have to pack the zeros. So in this manner, we can keep track positions of that 1 easily. You're just shifting it back and forth in scientific notations. Okay, that's why it's very useful in science. Keep track of very large and very small numbers. That's it. Okay. Bye-bye. Until next time, have a good day.